All right, so last time, yes. You'll know which one's the major product when you calculate the yield. Yes, right. It'll be either or. Yeah. All right. So last time we talked about chair structures, which one's more stable. All right. So a common cycloalkane there, and based on how it's substituted, you get unique patterns of stability here. Okay. So let's now talk about conformers of di-substituted cycloalkanes. Okay. So we're going to talk now about conformers of di-substituted cyclohexanes, sorry. So the big part of this is, can you draw both chair conformers, and can you tell me which one is more stable or less stable? All right. So that's going to be the highlight for the quiz next week. Drawing chair structures, stability of which conformer, this one or this one. Okay. So let's first look at trans 1,2-dimethyl cyclohexane. All right, so we got our wedge bond here, our dash bond. Okay, so this is trans 1/2-dimethyl hexane. All right, so naming these are pretty, I think a little more straightforward than linear alkanes. You don't really have to worry about what gets the one position, because it's usually, where the substituents are, right? So if you need more practice, please do homework 4, okay? Chapter 4 homework. All right, so let's draw the first chair conformer. All right, so it doesn't really matter where you put the numbers on this chair, as long as it's consistent, okay? So what I will do is, let's see, what should I do here? Okay, I'll make my point pretty clear here, okay? So this one, I'm going to choose 2 random positions, and in the other chair structure, I'm also going to choose 2 random positions, okay? So we know one is going downward, so this one could be our downward position, H3C. And then the other one is up. So we have to pick a substituent position where it's going up. So this one could be up too. Whoops, sorry. Like that. So notice here, they're still in the 1-2 position, right? 1, 2, okay? Now this one is di-equatorial. So remember what we said about equatorial? Oh, the methyl groups, they should probably be equatorial so we don't have 1,3 diaxial strain, right? So this one looks like a candidate for being stable. Now, if it goes to its other form here, we can tell how much it's going to go based on the value of delta G. So it's going to require energy going this way. So plus delta G. And then if you go back to the left form, that's less energy. So we're going to lose energy there. All right, so let's draw our alternate chair form. All right, so this time I'm going to just pick 2 positions here, like so. CH3. So they're both axial. So you have a situation where both of them are now axial. Now that's bad because it's going to bump into these hydrogens right here. Right, so these methyl groups will bump, and these hydrogens will bump with the top methyl group. So that's not very stable. So remember how we talked about sterics? Organic, that's a common theme here. So this one would be less stable And then this one would be more stable. And on your homework, there'll be a question where you actually have values of delta G based on what the substituent is. Is it a halogen? Is it oxygen? Is it methyl? Is it isopropyl? Or is it terbutyl? Okay? And the trend is the bigger the substituent, the higher the value of delta G, so the more positive it is. Okay? So this is saying, oh, what's the energy it takes to put my methyl group in the axial position? That's your delta G value, and it's usually positive. Okay, hydrogen usually doesn't cost anything because it's the base, it's the standard, it's what we compare it to. So it's usually carbon and other atoms as substituents. Oxygen, halogens, any alkyl group. Okay. All right, so that's trans 1,2-dimethyl cyclohexane. Now let's look at the cis example. So here, the only difference is you're going to make these both wedges or dashed. It doesn't matter if you make it dashed or wedged. So don't worry about that. So cis dimethyl cyclohexane. All right. So let's try drawing a chair structure and put both of those substituents in a 1-2 position and make them both either pointing both up or both down. Well, in this case, let's do it up because it's wedged. Okay? All right, so let's practice that. Let's practice drawing our chairs. All right. So this one, CH3. All right, so let's just use the edge here to kind of draw our substituents. So I got CH3, both pointing up this way for my cis example. All right, now let's try drawing our other chair conformer here. All right. Don't worry, they don't have to be the same, relatively the same scale. All right, so my position right here, okay, that's now over here, equatorial up. So remember, when we do a ring flip, the stereochemistry stays the same. So whatever's coming out at you, up or down, is still the same. But now it's equatorial going to axial or axial going to equatorial. So that axial now went equatorial up. Okay? And this carbon 2 right here, this is going to now be going up at this position right here. All right, because remember what I said last time? These two positions switch, and these two positions switch in the chair flip. Okay, so I went from kind of this obtuse angle down here, so this obtuse angle. Now I went to this inner angle right there, as we see right there. Okay, so there is a way to visualize this. If we model today, maybe we'll build a cyclohexane. We can see how those bond movements occur when you do a ring flip. All right, or maybe I could show a little. After we finish drawing these, maybe I could show a little video how the chairs interconvert like that. Okay. All right. Are any questions drawing these chairs? The positions could be confusing because how do you know which ones go where? But are any questions about that, Catherine? Yes.
When the next exam for the chair configurations, are we allowed to have the molecule kits?
No. Unfortunately, not. Any other questions? That's a good question, though. Yeah. No. Unfortunately, not. All right. All right, so let's do a different example now. All right, so we have our or a chair. Okay, so let's do a ethyl group this time. All right. Okay, so again, you might be asking, okay, we have this example. Cis 1 ethyl, 2 methyl, cyclohexane. All right, so notice in our previous example, we didn't actually label which one's more stable or less stable. And that's because what's the difference between them? Both of them each have only one methyl group in the axial position, so there's no preference there. So they're both of equal stability, so there's no difference in stability here. Okay, but now we have cis 1 ethyl, 2 methyl. So now that will change things, okay? So let's draw our chairs here. Okay, so let's just use the same idea. This is going to be our ethyl and our methyl here, both sticking up, and it becomes like that. All right. I'm going to flip these. Sorry, let me just change something. Oh, wait, no, that's right. Okay, so in this example, I kind of flipped the stabilities here. This is actually less stable than this one. So this will be, when we move in this direction, you're actually losing energy. And if you're forming this ethyl group here in the up position, in axial up position, that's actually going to cost you some energy. So we could draw this other chair structure. Okay. Now this one, the ethyl group, is going up equatorial, and the methyl group here will still be up axial this time. But which one is considered a little bit more bulky or big? Methyl or ethyl? Ethyl. More carbon atoms, more space it occupies, okay? So less stable, okay? And that's because bulkier group axial. Okay, so you want that bigger group to be equatorial, and we'll really see this in the next example with tert-butyl. Okay, so this is less stable and this is more stable. So depending on what I ask you, if it's more stable or less stable, you would have to circle one of these, and your explanation can only be one sentence. And you can say, oh, this chair conformer has the bigger group in the equatorial position. That's all you have to say. And you can say something like, there's no 1 diaxial strain. Okay, you don't have to, write a little essay about it. Just be short and concise and to the point, and you'll get all the points. Okay. All right. Are any questions on this chair? How we drew them? Okay. So today we'll work with the models and see how these chairs, so as an exercise, let's build a chair today in lab, and we'll see how these chair flips go, okay? All right, but any questions about the chair flips? I know it looks kind of weird right now because it's kind of hard to imagine how these bonds are rotating and how the other bonds move in response to that. But cyclohexane is very flexible and it can do this. That's why it's so universal and kind of organic compounds. Okay. Yeah, Catherine, what's up?
So if we had the Newman projections for the less stable one, would that be eclipse? Because of both your group is...
Yeah, so almost. So it's actually, it's because of if we go back, maybe we could go back really quick. If we go back to last time, so all the way down. So remember, it's not the eclipse that's the problem. In the chair, everything's staggered. So what's the problem is actually just being the gauche interactions here. So it's not eclipse that's the problem. It's this group here. So So remember, when two groups are 60 degrees apart, two carbon groups, we call that the gauche interaction. So it's this carbon group and this carbon group. So that's the gauche interaction, and that's primarily due to steric hindrance. Yeah. So it's actually not eclipsed. So this form is not has no eclipsing carbons or hydrogens. Another conformation we'll mention does have those eclipsed hydrogens, but not the chairs. Chairs are pretty stable. All right. Any other questions on that? No? Okay. So let's go over now. All right, this example. So this next example is a pretty interesting phenomenon. Okay, so say you have this bulky group here, tert-butyl, the bird's feet, and the methyl group, okay? So your first idea might be, okay, I'm going to draw both conformers. But one of these groups is so big that it absolutely despises the other conformer. So only one conformer is found. Which one do you guys thinks it is? So is my bulky group going to be axial or equatorial? Yeah. So this is the only conformer that this chair or cyclohexane adopts. So my tert-butyl group is pointing down, so I'm going to point it down here. Okay, and the methyl group is forced to be down in the axial position. So when a group is too big, unfortunately this only occurs for tert-butyl on rings, okay? This is the only conformation it will adopt. So this is called ring freeze. So you can actually freeze this conformation, and it might be possible to force it to the other conformation, but it doesn't do that at room temperature. So it's not cycling back and forth at room temperature, like in a bottle in the stock room or something. It doesn't go back between chair forms, and that's a consequence of the structure of this compound. So it has some kind of structure-function relationship there, okay? So what I like to say here, it's stuck in parentheses, okay, with the tert-butyl group in equatorial position. Yep, because it'll take 9 kcals to force this tert-butyl group in the axial position, okay? Yeah, so here I would say the T-butyl group here, it's too big or too bulky. And when that is in the axial position, you're going to get severe 1-3 diaxial strain. So too much steric hindrance. Okay, too much, it's just too high in energy, too unstable to exist, okay? And,
when you say too bulky there, you're talking specifically about the axial position?
Yeah, so it's too bulky, let me just put this in, let's say too bulky here to be in the axial position. All right, so it doesn't like to be in that position because there's too much repulsion or too much steric hindrance between the hydrogens, and the tert-butyl group, okay? So remember, we're always referring to these hydrogens here. So if that group is down there, it can't interfere with these hydrogens on the bottom. Okay, the only thing you'll see here is the methyl group interacting with these hydrogens, and that's the only negative effect of the methyl group being in that position. Now, if the tert-butyl was in that position, there'll be like too much of those interactions, and it's just too much that it doesn't prefer to be in that conformer at all. Okay, so it can't even go to that conformation at room temperature. Okay, so hopefully we're thinking about like organic. You kind of have to think about space, proximity, repulsion type effects. Where in our other chemistry classes, we usually didn't do that too much. Okay, it was more like quantifying and looking at just how reactions take place through just the atoms, right? Okay, so one last thing we'll talk about. We're going to do a 1-3 relationship. So we're going to do trans 1-3. Okay? All right, so let's draw one more pair of chair structures, and that might be it for this chapter. We'll talk about the conformations the chair undergoes besides just going to a chair. But here, let's make this one going down, dash down, and this one 1, 2, 3 going up here. So you see here, one is already axial, one is already equatorial. So if we do the chair flip, do you think there's going to be a preference for this one if the groups are both the same? No. So 1-3 is also that kind of relationship. If it's the same substituent, there's no preference. Of course, I won't give you that example because you can't circle which one's more stable. But if they're the same substituent, 1-3, and then also cis 1-2, trans 1-3, they will be there's no preference there. We could probably also compare cis 1-3, but we won't do that today. Okay, so here I'm going to point this one turns axial now, and the one in the third position will be right here, and that's going to go upwards, H3C, right there. All right, so look at both of them. One is an equatorial, one is an axial. So there's no preference for this chair, pair of chair structures, but we can name it trans 1, 3 dimethyl cyclohexane. All right, are there any questions on those chair conformations there? Any questions about those ones? All right, so the last thing we'll talk about, we're going to talk about the boat. We call it a boat. There's a boat conformer. And then we're going to talk about the energy diagram, how these changes occur over time. But are there any questions about these chairs? All right, so the best way to get a hang of this, practice, practice, practice. The homework will help you do that. I added a lot of chair type problems just to help us get comfortable drawing these things, okay? All right. All right, so boat conformer. So I guess we call it the boat conformer because it looks like a paper boat you build and try and sail it. That's fun. That's like a toy when you're little. Okay, so first let's redraw cyclohexane in the planar form. So draw the hexagon again. So boom, boom. All right, so as I draw this, you can draw it as well. Oh, don't worry, I won't draw any 3D models this time. No, that was no need for that anymore. All right, number it 1, 2, 3, 4, 5, 6. All right, and then remember here we kind of highlighted it, bolded it to show that we're looking at from a perspective, like kind of coming out at us. All right, and then here we had our H's coming out as well from our perspective. Okay. So now, and remember we did at position 1, move that one up. Position 4, move that one down. That's the chair. What if we move them both up? Okay. So this one, we're going to move this carbon up. So move it up. And also this one, move up. All right. When we do this, now we're not going to get the chair. We're going to get the boat. So let's draw the boat form. Okay. So it looks like if we took the cyclohexane and kind of brought it out of plane here. So it kind of looks like this boat. Kind of looks like the top half of like Batman's mask or something. Anyway, so the hydrogens that we pointed up, if you think about it, if we took those points up, what do you think the hydrogens are going to do? On those 1 and 4, carbons 1 and 4, those hydrogens, where do you think they're going to point now if we bring both those ends upwards in the same direction? So let's draw them. This hydrogen now will come out here. This hydrogen right here. Oh, but hydrogen has some shape here. These hydrogens now are going to be very close together. So that's not eclipsing strain anymore. That's steric hindrance. Okay, so they're really close now. So that's the repulsive forces that we get from two atoms trying to be in the same place at once. It's not due to just repulsion. It's the fact that if you have two 3D objects and they can't, you can't squish them together, they're going to repel each other and bounce apart. All right? Just like two marbles, when they come in contact, they collide and go in opposite directions, right? They don't just like meld or melt together. All right, so this is a kind of steric strain, but it has a specific name because we are in a ring. So this is what we call, so when two groups across the ring interact, that's something called transannular strain. All right, so this strain is not a problem for cyclohexane because it just adopts the chair. But when you go to like 7-membered rings, 8, 9, 10, and then like 12 and 14, this particular interaction becomes a problem. So this is a problem for big rings, or for our cases when we have a very deformed conformation for cyclohexane, the boat. Okay. So the other hydrogens, they stick out over here. All right, so let's number them again. Let's just color code it. 1, 2, 3, 4, 5, and 6. Okay? All right, so what do you think is going to happen with the other hydrogens? They're not going to be staggered like in the chair. So now they're pretty much lined up, okay? And what kind of strain was that when they're completely lined up behind one another? What kind of strain was that one? Torsional. Yep, torsional strain. So see here, they're lined up, so they're eclipsing each other. This is now through electron-electron repulsion. So this is going to be not a very good interaction. And then this is not drawn to scale, but these are both sticking up and above. So this H and this H. Now it may not look like they're eclipsing, but they are relatively the same distance away from these ones I've drawn below, and they're interacting as well. So this will actually be now a torsional strain too. So these ones here, we now have torsional strain. Okay, and this also happens for the hydrogens on not only carbons 2 and 3, but what other two carbons? Yep, so this is torsional strain from the H's on carbons 2, 3, 5, and 6. Okay, it doesn't interact with 4 because 4, they're kind of bent out of plane, so now they're not eclipsing with those, but what you did there, you introduced transannular steric strain, so that's why the boat conformation is not the most stable. Okay, so that's all I want to talk about the boat. Are any questions about the boat? So, be able to draw the boat. So I drew it in pretty good detail here. So, able to draw it like that, and then the chair. Those are the only two ones. So I'll ask the common question, be like, okay, here's the chair, here's the boat. Which one's more stable, and can you explain why?
So when you say that the boat conformation is not the most stable, do you mean that it is the least stable? Or
No, I'm going to show you now in this little energy graph. I'll tell you, we'll note which one's, how stable it is to the chair. Yeah.
So sometimes the chair can be less stable than the boat?
No, so the chair is always the most stable.
Oh.
The boat is just a little bit higher in energy.
Okay.
Yeah. Good question. All right. So any questions about the boat? Now we're going to draw all these conformations. So some of these conformations I draw, you're not responsible to draw, but you should note that these are conformations that are part of the process of the cyclohexane becoming a chair. Okay? All right. So the last thing we'll draw is the chair to chair interconversion energy diagram. All right, so let's make some space here. All right, not the very best line. So energy, again, increasing energy on the y-axis. And then on the x-axis, that's how our bond angles, that's how the chair is changing as time goes on. So again, this is reaction coordinate. All right. So the reason I draw these diagrams is because we'll see them a lot, especially for reactions of the substitution / elimination type. So they'll become important then too. All right. So our lowest point here. So let me just draw a little bit like this. All right. Always nervous drawing these graphs because I'm not a great artist, okay? So the lowest point here, this is, let's just draw a dotted line to indicate that this is the lowest energy point. Oh, God, okay. Sorry, I got to fix this a little bit. Make this lower, like that. Okay, so the lowest 2 points here, so here and here. What form of cyclohexane do you think that is? So what's the most stable conformation we've been drawing for, I guess, the past 2 to 3 lectures here? Oh, no. So think of cyclohexane. Don't think of anti or syn. Think of like chair, boat. Chair, yeah. So I know we're kind of, we need to think about, Newman projections. Well, let's not think about Newman projection for cyclohexane. Okay, so here this will be the chair. And on the other side, we just draw the opposite chair, the chair flip. So they're both chairs here. All right, so the first thing the chair would do to go to the other chair is it will form a very high energy conformation. And this is called the half chair. So let's just say half chair right here. Okay, so this costs 10.8 kcals per mole. All right, so the half chair looks like, I don't know, it kind of looks like what a lazy boy would look like when you extend the legs. Okay, so let's just draw it like this. Boom. All right. All right, so that's the half chair. Only one end of the chair has been moved up or down like that. See that? And so this relieves the bond angle strain. So this is now 109 degrees bond angles. All right. So remember, cyclohexane has 120 if it's in the planar form. So it releases some bond angle strain, but it's so high in energy because now there's still eclipsing interactions. Okay. And when you deform one side of it, you're going to mess up some of the other bond angles too. So those may go up or down. So, but in this case, we're trying to relieve the bond angle strain. So that's why we moved it right there. All right. So if we compare this line to this line, so let's look at this line right here. All right, so this line right here, the distance from the chair to this bottom part right here that we'll get to, this is 5.5 kcals per mole. Okay, so that's the energy from what we call the chair now to this first point down here. This is called, all right, this one's hard to draw. It's called the twist boat. You don't have to draw that, okay? I'm not gonna make you draw it. It's very hard to draw actually using the model, so I'm not going to attempt that. I'm going to draw it. It's going to look weird, okay? So this is the twist boat. So you have your typical angle here. The one's going to come across to form a bond here, and then this bond is going to go back and behind like that. I don't know, so I guess it looks like sort of like a fish or something, but that's the twist boat, okay? You don't have to draw that. That's the second most stable form of cyclohexane. I always get them confused because I'm like, why is this one the most stable? It looks distorted. Wouldn't it be the most unstable? So it's actually the second stable form of the cyclohexane conformations, but you don't have to draw that one, okay? And then it's also right here. So the other twist boat is right here. So here is also the other twist boat. So that's a twist boat. And this is the other twist boat. So you're just going to flip the bonds here a bit. So that's why I don't require you to draw these because it's kind of weird here. Okay. All right, so you see how the crisscross bonds, they kind of just alternated now. So that's the other twist boat. Okay, so the twist boat is higher in energy than the chair by 5.5 kcals, so not a lot, okay? But then now we come to what's the intermediate between the twist boat and the other twist boat. All right, so this one, this energy right here, this is 1.4 kcals per mole. Oh, sorry, let's just put that below. All right. Well, I think we know what the other peak is, but what's this one? Which conformation we're missing that we didn't talk about yet? Well, we didn't mention here yet, but we just talked about it. The boat. So that's the boat conformation here. So that's the it's not the most unstable form, but it's one of them. Okay, so it's the unstable form before going to the other chair, and then right here we will have the other half chair conformation like that. And still, this is 109 degrees, so not the best, but that's the other half chair. And then you can see how the half chair, that pointed up part, what represents the other chair form, the other side as we go to the final chair foot. All right, so takeaways here. Most stable, what conformation? Chair. Okay. And then the boat here is the one of the more unstable states of the chair, of the cyclohexane. Okay. Don't worry about twist boat, but that's how it converts. It's not just chair, boat, and then chair. There's these other conformations that cause the energy to go up and down. Okay. All right. That's for chapter 4. Any questions on chair conformations? No? All right. Not too bad. Okay, so now, first let's take a break, 7-minute break, and then we'll start talking about diving into stereochemistry, okay? So next week, just focus on cycloalkanes. Stereochemistry will have to come a week later. All right. It's either too cold or too hot. Oh, least stable is that? Yeah. Okay, we'll probably just mark that down. Least stable. Don't worry. Well, you should be able to know how many different products you can get. But most importantly, this is how many you can get. Yeah. Is it? No. No, man. You gotta go. Just do the activity with us. Then you already finished most of the stuff, so we'll just do the activity. Okay? We're going to work with models and do this part. I know. I see that. All right. Just stay for a little bit. Okay?
I didn't do all that. But this one, yes, I'm pretty sure. I said 4. Yeah, you did it right. I just added that. I just never put the and he's like I only did the percentage. Oh, this is what did you want this? No. attaches, and this one is like everyone.
So the initial phases, you're just not making everything like.
The one that's being, and three that are checked out. So right, yeah, three.
So there's, since they're all metals, there's 35 genes in each one, and they're all primary, so it's one times nothing. Okay. And then B is tertiary, so it's five. And so yeah, I got 14. Okay. That's right. Exactly.
you're looking at this way and see, you also see the compound that is, whatever it is. Even if it is just very simple, right? And then you know, and then you do two compounds
Yeah, that's fire, that's fire.
Ugh. All right, so let's just summarize these transformations of the chairs. Chair, boat, twist boat. By watching this little animation here, I'm pretty sure they go through the conformation. So let's see how much they go through. Okay, so we got the half chair. See the half chair? It looks like a lawn chair. The twist boat, it's crossing over the bonds. Back to the boat there. Another twist boat, half chair. And then lastly, the other chair conformation. Okay, so you see how it wiggles around. It just does its own thing there. Okay? All right. So these videos are available to you if you need a visual representation of how these bonds are like going up, down, all these different conformations. Please utilize that. Yeah, Catherine. Oh, so on Canvas, there should be a module videos, additional videos. Yeah, so I could probably bring it up too. Let me see if I can bring it up. Do I have Canvas up? No, I don't. All right, but it's on Canvas. Guys, if you need me to show me we're on Canvas, look at one of the modules. It should say like additional practice videos, simulations. There should be a website that has all of these. But if you have an iPad, you can actually download this app, Tap Chem. There's a student version too, and you should have access to all of these. So Tap Chem. So there's an Apple app. Unfortunately, only for Apple. So you can use it on your phone. So you download this app that has all these videos available. All right. Okay, now we have to talk about, I think, one of the hardest chapters we'll encounter, stereochemistry. Okay? So this is chapter 5. Okay, but quickly, I wanted to recap here. The chair, most stable. Half chair, that's the least stable. Okay, so chair is the most stable here. Half chair, least stable out of all the conformations. Okay, so let's talk about stereochemistry. So stereochemistry is, so remember we had structural isomers? We have stereoisomers too. We're at a different space. This is not the same as conformers, because in conformers, you usually have the same spatial arrangement of atoms initially, and you just rotate them around an axis. In stereochemistry, you can't do that to get the other stereoisomers, so that's a little bit different. All right, so first we're going to talk about chirality. So what is a chiral molecule? Not sure you heard this term. May have heard this term in biology, actually. Has anyone heard chiral before? So chiral is any molecule that does not contain a plane of symmetry. All right. So when we think of plane of symmetry, right? Think of this globe here. Is there any plane that I can draw through this globe that splits it in half? What do you guys think?
I think it's the equator.
Yeah, so you can split it this way or this way. That's the point of symmetry. So a globe is not symmetric. A globe is not chiral. Okay. So molecules that don't have this feature will be something we call chiral. Okay. They have the property of chirality, and it's this definition right there. It has no symmetry elements. Okay. So what this means is molecules here, they are not superimposable. Do we all understand what superimposable means? It's like you try to place your hand over your hand, right? They're not superimposable. They don't completely line up or overlay with each other. They're not, it's not superimposable. I think of another term, I guess. Overlay or, like overlapping. So my hands don't overlap with each other because they're mirror images. They're chiral, non-superimposable mirror images. Okay? So we say not superimposable or overlapping on its mirror image. Okay. All right. So that's what chiral means. Okay. So we're going to spend some time thinking about that. So now let's talk about the opposite of chiral. That's what we say, achiral. So what do you think an achiral molecule is? Yeah, it has some symmetry element in it that's symmetrical. Makes it symmetrical, okay? So it's any molecule that contains a plane of symmetry. And is superimposable on its mirror image. All right. So there's a way to know if molecules are chiral or achiral, and they have something called a chiral center. Okay. So chirality or being chiral, that's the property. So this next part, a chiral center, if a molecule has a chiral center, that makes it chiral. Okay, so that gives it its property. So let's go over chiral center now. All right. So chiral center is also known as a stereocenter or a asymmetric. All right, I always mess up how to spell this. Symmetric center. Okay, for most parts, it's only carbon atoms, but it can be carbon, sulfur, phosphorus, but not nitrogen. Nitrogen can't do it. There's a reason for that, but it's a special property of nitrogen. I won't go into it. You can ask me separately about that, okay? But it's mostly carbon for us, okay? So a chiral center is any atom, all right, atom that is surrounded by 4 different groups, okay? So what this means is it's a tetrahedral carbon atom with 4 different atoms bonded to it. All right, not just atoms. It could be groups of atoms, like alkyl groups, rings, halogens, etc. Okay? So chiral centers here give rise to being chiral. Okay, so chiral centers, they give the property of chirality in a molecule. So this will become important when we talk about what chiral molecules do. How do we tell if something is this stereoisomer or this chiral center, or this chiral molecule? Okay. So our first thing we should be able to do is to identify molecules. Are they chiral or are they not? Okay. So this only applies to molecules. So this applies to all molecules with one stereocenter. Except the means are chiral. All right, so what about two? Well, sometimes if something has two chiral centers, it can be chiral or it can be achiral. So there comes a time when some molecules, they will have planes of symmetry but they have chiral centers. Okay, if they meet those two criteria, we'll see that they are actually achiral. Okay, so that's why I said one stereocenter, they will always be chiral as long as there's only one. Okay, at least one. If there's two, maybe. All right, and then so forth and so forth. All right, so let's do some examples here. Let's look at this molecule. All right. So, do you think this molecule is chiral or achiral? So let's look at the carbon atom with multiple substituents. All right. So, if we look at the carbon atom, where I drew the rest of the bonds there, does that have 4 different groups? Let's see. Well, that's 1. That's 2. Oh, look at this one. 3. This ring. Let's just track it back to this spot, okay? This side is the same as this side. So 3 and 4 are the same. So we're going to say achiral. Right? Because branch 3 is the exact same as branch 4 if we trace it around, or to that middle point I saw, or if you trace it around in a circle, you have the same type of atoms in either direction. So that's not a different group or substituent. So this carbon here, so the carbon I'm looking at exactly is this one in red. That one is achiral. All the other carbons have 2 hydrogens at least, so that's not chiral either. So this molecule is achiral. All right, so let's try this one. Let's do another one, okay? Let's try this. Now, does this molecule have a chiral center? Yes. Okay, so let's put a little asterisk by it. So this carbon on the top right here, that's a chiral carbon, all right? So here is my chiral carbon atom right here. Okay, and that's because this one has 4 different groups. The rings now are not equally, they're not equal on both sides of the ring, right? One goes to a carbonyl group, and the other just has carbon atoms. So that's not the same, okay? So in order for both sides of the rings to be the same, they have to have the same arrangement of atoms. Oh, CH2, 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 CH2. Well, one side has CO, CH2, CH2, and then the other one has CH2, CH2, CH2. So that's the point of first difference. So that's a substituent, okay? So let's just number them again like we did. Methyl is 1, hydrogen is 2. This group is different from 4 right here. So they're not the same. 3 is not equal to 4. So we have a chiral compound. All right, so that's another example. Let's do another one. So basically you could say anything that's symmetrical is going to be what? Yes, so let's look at this example. 3-bromopentane. All right, and let's look at this one. All right, which one of these is chiral? The one on the right. Why not the one on the left? So we have bromine in the center, right? But what's wrong about those two alkyl groups? Are they different? If we go back, if we look at this center, right? Are the two carbon groups bonded to it? Are they any different or are they the same? They're the same. So that's achiral because these two groups are equivalent here. And then bromine here would be chiral. 2-bromopentane would be chiral because there's a chiral carbon right there. Okay? So this adds to our layer of complexity in terms of stereoisomers. So we have even more isomers now. Okay? So it's not just constitutional isomers of different connectivity. We have stereoisomers too. So that adds up to the wide variety of different compounds we can have. Okay? All right. So let's do a few more examples. Okay? Let's do some actual real type examples by natural products. All right, so these are things you could find in nature. They're in perfumes. You may notice some of these as common smells of every day. So let's talk about this first one. A perfect example here. This is called carvone. All right, can anyone tell me where the stereo center is at, or the chiral center is at? Is it anywhere near the double bonds? So it won't be at the double bonds, right? Because how many different groups are around double bonds? 3, right? Only 3, so that doesn't count. Alkenes are planar, so they have like a plane of symmetry going on there, just going through all the atoms. It might be hard to see. I'll explain it more. I'll explain it better when we talk about certain stereoisomers. Okay, so the chiral center is here, right? That has 4 different groups. You have an alkene going on to the outside here, alkene in a ring here, and then here you have a double bonded O, so those are 4 different groups, okay? And what's the other group that's not shown? Hydrogen right here. All right, so carvone, this isomer has a specific smell, so different stereoisomers, they can have a wide different effects in the body and how we interpret them with our senses. So this one actually smells like spearmint. So this comes from spearmint oil. Yeah, so what's better, just making this compound, extracting from a tree, or trying to get spearmint gum and extract all that? I don't think that might not even be pure spearmint either. It might just be something that smells very similar to spearmint. Okay, so that's the smell of spearmint oil. Very fragrant compound, very nice to work with. But I don't know if you get anything done. You'll just smell everything all day. Okay. All right. So this one, we're going to have a series of rings here. All right. So there are 3 chiral centers in this one. Can we guess where they are? All right, so remember there's also H's in some of these, okay? So if you don't see the H, just think, okay, it has an H, so it must be different. All right, so we have one right here. Does anyone know where I can find the other two? Yes. Yeah, what about the last one? To the left. Good. So those have 4 different groups based on the structure here. All right, this has a very interesting name. Newt ketone. All right, this is from grapefruit. You see here, these compounds are they look very organic. Okay, lots of carbon-hydrogen bonds, so no wonder that these readily metabolize through our body, through the lipid membrane. Okay. All right. So, any questions how we determine chiral centers? Don't worry about if you know how to do this yet. We will do this on probably not next week's quiz, but probably maybe the week after that. Okay. Any questions? All right. So good practice here. Just draw a bunch of compounds, draw a carbon atom bonded to 4 different things, and convince yourself that that's 4 different groups, and that's a chiral center. Okay. So we'll go more into detail why these are chiral, and they basically they can't superimpose on this mirror image, and we'll talk more about that when we talk about actual stereoisomers. Okay. All right, so one last thing I want to cover for the quiz here, enantiomers. Okay. Have we heard of that term, enantiomers? Yes, okay, good. So those are the specific names to the chiral forms of molecules, okay? So, enantiomers here, they are mirror images of chiral compounds. That are not superimposable okay. So the reason why they are mirror images is because they are identical, but they do not interact with light in the same way. That's why they're mirror images. They look the same, but they don't necessarily interact with light the same, I would guess. Okay? So, we have left hand enantiomer and right hand forms. Left hand and right hand forms. So they're like our hands, right? We have a right hand and a left hand. They're mirror images, but do they superimpose? No. You can't do it this way. They're not in the same orientation. They don't superimpose here. So our right and left hands are like enantiomers, okay? They have a right form and a left form. All right. So how do we tell if we have enantiomers or mirror images of a chiral compound? Well, we expose it to light, okay? So enantiomers have a specific definition here. They rotate, so I'll talk more about this. They rotate plane polarized light, okay? If we don't know what plane polarized light is, I'll give you some examples. So they rotate it in specific ways. So they rotate this light either clockwise or counterclockwise. All right, I'm just making those 2 words. Okay, so for example, when you capture light with your camera, right? You're not capturing you're capturing all forms of light, and your camera has special filters, all right? They're called parameters. They filter out certain aspects of light, right? You don't want blurry photos. You don't want glares in your photos. So that your photo is actually using this technology to filter out light and get only a certain plane of light. So remember, light moves in waves. Do you remember waves? Oscillates back and forth like EKG in waveform. So what light does, what your camera does, it takes in light of a particular orientation. So it's only rotating or oscillating in a specific plane, and that's how your pictures come out so good. Is my guess. Okay, so plane polarized light here. So we kind of think about it. Plane. So this is just some examples. You actually don't need to copy this down if you don't want to. Just some examples of where this is important. Okay. So where do we see this here? So used in photography, used in optical microscopes. So how do you magnify things? Well, you're only taking a portion of the light to enhance an image, okay? So that's used in optical microscopes. And then next one here, chemical analysis. So this is what we're talking about. And then liquid crystal displays, LCDs, how you generate images on the screen. So we're capturing the light through these materials, and that is what we're doing with the light here. So we are exposed to light, but we don't use all of the light. We focus it and only use certain parts of it, okay? So let me give you a little diagram here what I'm talking about. So here's plane polarized light. So let's draw a circle. All right, so let's draw this line here. This line comes, so say this is my light source, okay? And I'm rotating this axis. So this is my initial plane of light. All right, and I can rotate this plane clockwise or counterclockwise, okay? So let's say we rotate it clockwise. All right, so we can rotate it this way or this way. But based on my picture here, I rotated it clockwise, okay? So this angle here of rotation, that's called alpha. So that's our angle of rotation of plane polarized light. All right. And then here, this dotted line, that's our observed plane. So that's what we see. So I kind of hard to explain. We don't necessarily see this light. I guess that's the light we see after it goes through a filter. But it doesn't look any different to us, right? It might not look any different to us. But when we look through a lens, it'll be different, okay? So our detector detects that change in rotation or angle. So that's our observed plane of light. It'll be easier if I had actually the instrument we use. Then it'll be a lot easier to explain, okay? So if it rotates the light clockwise, that's called dextro-rotatory. All right? So this isomer, if it's the dextroisomer, it rotates light clockwise, and we denote that with a positive sign in parentheses. So this is the plus and antimer. You can only tell if it's plus or minus by recording the angle of rotation of the light, okay? And then the opposite one is levorotatory. Okay, so this is counterclockwise. All right, this is the negative. This is usually denoted with the negative and antimer. Okay, so sometimes this has the designation of L in front of it. Sometimes this is the designation of D right here. Now, I gotta be careful because this notation right here, D and L, also applies to sugars, stereochemistry of the sugars. So that's completely different, and I'll talk about that another time. All right, so one thing I want to, before we take the quiz, one thing I just want to mention, just wrap up here. So if I have both enantiomers, they have identical, so both enantiomers Remember when we said like, oh, the more branched alkane has the lower boiling point. They have different physical properties, right? Well, enantiomers, they don't do that. So they look almost the same. So they have identical physical properties. Okay, so they would have like the same boiling point. So same boiling point, density, etc. But they rotate plane polarized light differently. Okay. All right. So we'll talk more about this in lab today. But for now, let's clear our desk and let's take the quiz.